So in 1.3, we're going to be shifting our graphs. When we add 2 to the outside, so it kind of goes through the shifts and the transformations one at a time, but when we add 2 on the outside of our parent function of our graph, it would move the graph up 2 units. Now it's a little bit different when we subtract on the inside. So this is still an x squared graph, but we're subtracting 2 on the inside of our parentheses. Inside is a horizontal shift. When we subtract, it goes to the right. So it gives a graph of an example for each one. So when we add 2 on the outside, just shifts our parent function up 2. So our parabola would just move up 2. And then if we subtract 2 on the inside, we would just move our parent function, our graph would just shift to the right too. So on page 5, it has all of the vertical and horizontal shifts. So if we add on the outside of our parentheses or whatever our parent function is, it could be an absolute value, it could be a square root. If we're adding on the outside, we're shifting our graph up that many units. If we're subtracting on the outside, that would go down however many units. On the inside is when we move horizontal. So if we're subtracting on the inside, it would be to the right. And if we're adding on the inside, it would be to the left. So this should all be a review. You guys should have seen these before, kind of understand how shifting graphs work. It's really just memorization here. So just got to memorize these 4 things to know which way your graph is moving. So in example 1, it says use the graph of x cubed to sketch the graph of each function. So our x cubed graph looks like this. This is our parent function. Now we're going to take our parent function, we're going to shift it however our equation or however our new function says. So when we subtract 1, which way does our graph get shifted? Down. Awesome. We're subtracting 1 on the outside, so we'd move down 1. So we just take our parent function, shift it down 1. So now our new graph would look like this. And then for B, when we add 2 on the inside, which direction does that move our graph? Left 2. And then when we add 1 on the outside, which direction does that move our graph? Up 1. So here we have 2 transformations. Whenever you have multiple transformations happening, you always want to go from the inside, like closest to x, to the outside. So start with what's happening directly to x, and then apply your transformations kind of inside to outside. Here it doesn't matter. You'd end up no matter what the order is, but when we start to get into reflections and stuff, you always want to start from the inside when you apply your transformations. So we're going to move to the left 2, and then go up 1. So we've got our new center, and then we can just draw our x cubed graph from there. Next, we're going to talk about reflections in our graph. So when we multiply by a negative, our graph gets either reflected on the x-axis or it could be reflected on the y-axis. And when we reflect, it's the mirror image. Next page talks about the 2 different types of reflection. So if we are multiplying by a negative on the outside, it's going to be on the x-axis. So if it's outside of the parentheses, or like outside the x squared, outside the absolute value, outside the square root, it's a reflection on the x-axis. If it's happening directly to the x, so inside, it's on the y-axis. So So let's look at some examples. It says compare the graph of each function with the graph of the square root of x. So I'm going to start by graphing our parent function, the square root of x. So if you know the shape of the square root of x, you can graph it or just plot some points. If I took the square root of 1, I'd get 1. If I took the square root of 4, I'd get 2. So this would be the shape of our square root of x graph. So this is our parent function. Let's graph A. So when we multiply by a negative on the outside, it's a reflection on the x-axis or the y-axis? What do we think? Outside would be x-axis. So our x-axis acts as the mirror, and we just flip it along the x-axis. So it just flips upside down. So our new graph would look like that. Let's graph B. When we have a negative being multiplied on the inside, that's a reflection on the y-axis. So now my y-axis is going to act as the mirror. I'm going to take my parent function, which is that blue graph, and just flip it along the y-axis. So I'm just going to switch the points over in the negative direction here. And that would be my graph. Now with C, we have multiple transformations happening. When you have multiple things happening, you always want to start from the inside and go out. So starting with x plus 2. X plus 2 shifts our graph which way? We're adding 2 on the inside. Which way? To the left 2. Awesome. So to the left 2. So we take our parent function, shift it to the left 2. So I'm just going to kind of do a little rough sketch of my graph here. This is how it would be, but we have one more transformation happening. I have a negative on the outside. So negative on the outside means that it's a reflection on the x-axis. So now we just flip it along the x-axis. So I take all of those points, x-axis now acts as the mirror, and I flip it along there. So this would be my graph for C. So if you have multiple transformations happening, you always want to start from the inside and go out. And then just apply one transformation at a time. Now with reflections, there's one case that we have to be careful with. If I had something like the square root of negative x plus 2. When you have a shift left or right and a reflection on the y-axis, so it would flip kind of left or right here, we need to be careful. One way that we can do this is I would take the negative out from our term here. So it would be the square root of negative x minus 2. And then we would apply our transformations from here. So we would have a negative, which is a reflection on the y-axis, because it's still inside the square root. So it's a reflection on the y-axis. And then minus 2 would mean that we go to the right. One way that you can always check to make sure you did your reflections or your transformations in the right order is you can always just plug in points. If you start with your parent function graph, you can plug in values for x into your new function here or here, and your points will plot in the correct spots. When you plug in numbers for x, get values for y, it'll end up graphing correctly. So you can always just double check your work by just sketching it really quick. Last two transformations that we have are shifts and shrink, or stretches and shrinks. So if we multiply by a number that's greater than 1 on the outside, it's a vertical stretch. So if you're multiplying by a constant number that is greater than 1 on the outside, it's a vertical stretch. If you're multiplying by a number that's in between 0 and 1, so like a fraction or a decimal, that would be a vertical shrink. It's the opposite when the constant's on the inside. So if I had something like 3x squared, meaning inside of our parent function, if it is greater than 1, it's a shrink, a horizontal shrink. If it is less than 1 or in between 0 and 1, it would be a horizontal stretch. So when it's inside, that means that it is going to be horizontal. Just like how if it was adding or subtracting inside, we moved it left or right, so we moved it horizontally. If we're multiplying by a constant inside, then it's a horizontal stretch or shrink, and it's always the opposite of what we think. Example 3, we want to compare the graph of each function with the graph of the absolute value of x. The absolute value graph is a V shape. So it'd be a V shape looking like this. Now if we multiply by a number more than 1 on the outside, what type of transformation do we have here? Vertical or horizontal? Vertical. Outside is vertical, so it'd be a vertical stretch or shrink? Stretch. Since it's greater than 1. So vertical stretch, just think about it if you had like a rubber ball and you were stretching it out vertically. We'd be stretching it so we make it skinnier. So it'd be, I mean, you can plug in numbers for x and get your values for y. Or you could just sketch it. As long as you know that it's getting skinnier when you stretch it out. Now when we multiply by 1/3 on the outside, again, outside is vertical. This would be a vertical shrink. So if you need to, plot the first couple points so you see how much it's shrinking. But if you shrink something vertically, you're squishing it down. You're like compressing it, so it's going to get fatter, I guess. It'll get wider quicker. So if I plugged in 1, I'd get 1/3. If I plugged in 2, I'd get 2/3. So our graph would kind of look like this. Still have that V shape, it's just wider now.